As of 1961, many of the elements we now see on the periodic table were already discovered. Thomason, Rutherford, and Bohr had all done their experiments to tell us about the parts of the atom, and we knew where those parts resided. Protons and neutrons in the nucleus and electrons on the outside. We knew that electrons had little to no mass. We knew that the nuclear charge, or protons, was what determined the identity of the atom. However, the mass of individual atoms was always relative, and there was a lot of disagreement on what element each atom should be compared to. So in 1961, an international committee agreed that the mass of 1 mole of carbon-12 would have a mass of exactly 12 grams. So each mole of protons and neutrons have a mass of 1 gram. These masses, or molar masses, can also be reported in atomic mass units, or AMUs. So if each proton and each neutron has a mass of 1 AMU, how can the mass of elements be decimal points? Is it because of the mass of electrons? Is it because neutrons have a slightly greater mass than 1 AMU? No. It is because while each atom of an element has exactly the same number of protons, their masses can change due to differences in their number of neutrons. Atoms of the same element that have different masses are called isotopes. In a sample of any element, you may have several different isotopes. A mass spectrometer is a device that separates atoms based on their masses and allows you to see what percentage of a sample is one isotope versus another. We use these percent abundances to calculate a weighted average of the mass of an element. To calculate the average atomic mass of an element, multiply each mass by its percent abundance. Then add up all those small parts to have the weighted average. For example, if an unknown element, element X, has 3 isotopes in its sample, its mass spectrometer might look like this. From this data, we can make some assumptions. First, that X20 is the best proton to neutron ratio and therefore has the least amount of energy or is most stable. Conversely, that X21 must be the most unstable since it has the least percent abundance. We will talk more about isotopes, radioactivity, and stability later in the year. To calculate the average atomic mass of element X, we will multiply each mass by its percent abundance in their decimal form, then add up those parts. So, doing some calculations, we find that element X has an average atomic mass of 20.243 AMUs, or 20.243 grams for every 1 mole. If we were asked to identify element X, we would look on the periodic table for an element with a mass near 20.2 AMUs, which we would find is neon. We can also find an element's percent abundance using some algebra. Chlorine has 2 known isotopes, chlorine-35 and chlorine-37. If we want to find each isotope's percent abundance, we could do so by keeping in mind some things. First, that when added together, their parts have to equal the mass on the periodic table, or 35.453 grams per mole. Second, that both percent abundances have to equal 100% when added together, or their decimal forms have to equal 1 when added together. Therefore, if we assign 1% abundance the value of X, the other must equal 1 minus X. If we plug these values into our original formula for percent abundance and do some mathematical magic, we find chlorine-35 occurs 77.4% of the time, and chlorine-37 only 22.6% of the time. The average atomic mass on the periodic table can also be applied to whole compounds. The sum of the average atomic masses of all the atoms in a compound is the compound's molar mass. Molar mass is also known as formula weight for ionic compounds, or molecular mass for covalent compounds. So, for ammonium sulfate, which consists of 2 nitrogens, 8 hydrogens, 1 sulfur, and 4 oxygens, the formula weight would be 132.16 grams for every 1 mole. For angelic acid, a covalent compound whose formula is C5H8O2, you have 5 carbons, 8 hydrogens, and 2 oxygens, and would have a molecular weight of 100.13 grams per mole. You'll notice that for each element, I used the molar mass from the periodic table and pulled away only 2 decimal places from it. This is a generality. Some teachers or professors prefer that you match how many significant figures are in the problem, or even tell you to use all of the numbers from the periodic table. Check with your teacher or professor on how many decimal places you should use.